Before we can go ahead and start solving some of these game theory games out, we need to take a look at a few of the assumptions and what type of games we are interested in looking at. So two assumptions that we have right here. Number one, preferences are clearly defined where the objectives of each player are well known. So every single player that we take a look at in each of these games, they know exactly what they want. They want to get the highest payoff for themselves. Each of these players are going to be seen as very selfish. They only want to go ahead and get the highest payoff. They really don't care about the other person or hurting about the other person. They just want to get the highest payoff, highest dollar amount for himself or herself. Assumption number two, players are going to rationally choose strategies to achieve their objectives. Players make decisions that are consistent with their goals. So in order for them to maximize their payoff, they're going to choose a strategy that is going to give them that highest payoff. So two assumptions that we need to be aware of that are sort of tied along with one another, that players are always going to choose the strategies that are going to give them the highest payoff. They don't necessarily want to hurt the other player. They are only interested in seeing what is the best for himself or herself. Also, when we go ahead and solve these game theory games out, we want to go ahead and note that the vast majority of games that we do take a look at are going to be non-cooperative games. So the two players that we take a look at, they are making their decisions by themselves. They are not allowed to communicate with one another. So player number one, he or she chooses their strategy. Player number two, he or she chooses their strategy independently of one another. They cannot talk or communicate with one another. So do keep that in the back of your mind. These games are going to be seen as non-cooperative. So what type of games are we interested in solving? The first type of game and the more sort of common type of game are going to be simultaneous move games, where actions occur at the same exact time. So player one, player two, player A and player B, they're moving at the same exact time. They're choosing their strategies simultaneously. Examples of simultaneous move games include a lot of sports. So soccer, football, basketball, both of these sort of teams, defense and sort of offense, move at the same exact time. So they are moving at the same exact time, and we can model this with some type of simultaneous move game. In order to model these simultaneous move games, we're going to use something called game matrices or game tables in order to see how we can sort of take a look at that. The second type of game that we are interested in solving is not as common as simultaneous move games, but there are still a few notes and implications that we want to talk about. They're going to be called sequential move games, where one player moves first and then the second player moves right after him or her. And this is going to be a little bit more of a different game because sometimes there can be a first mover advantage or a second mover advantage in some games. Examples include a lot of sports as well. So golf would be an example of sequential move games, and also a lot of board games. So things like checkers, things like chess, things like Yahtzee, these are all sequential move games. And in order to illustrate these sequential move games, we're going to be using game trees. It's also called some type of extensive form analysis. So not as common as the simultaneous move games, but we will work with a few examples of these sequential move games as well. So one thing that I like to do before we actually go ahead and learn how to solve out these sort of these games right here is to go ahead and show you an example of a game and see if you can come to the correct solution. So let's go ahead and do an example of a simultaneous move game. And like we said, this is going to be modeled with a game matrix or a game table. So let's go ahead and build up a game table. So it's going to look something like this. So bear with me just a little bit as I build this table up. We have $1, $1 right here. We have $0, $3. This is going to be $3, $0. And this is going to be $2, $2. We have the strategies, which are yes and no. So very simple game, yes and no. And then we have players. So let's go ahead and just say maybe random person, Diego, and player number two is Paola. So Paola. So as we can see, this is going to be a simultaneous move game where each of these players are moving at the same exact time. It's a game matrix, it's a game table. And once again, we still have all 5 components of a game that are applicable. We have the players. We have player number 1, who is Diego, player number 2, who is Paola. We have information, which is perfect information because each of these players knows exactly what's going to be happening in this game right here. We have the strategies. So Diego has a choice of choosing yes, choosing no. Paola also has the same strategies, yes and no. We have the outcomes, so we can come to 4 conclusions or 4 outcomes. What happens if Diego says yes and Paola says yes? Then we get to come to this outcome number 1. What happens if Diego says yes and Paola says no? Then we have outcome number 2. We're in the second box right here, and then so on down the line. Outcome number 3 and outcome number 4. And then finally here, the final component are the payoffs, and the payoffs are denoted as dollar amounts to each of these players. The first number that you see is always going to go to player number 1. So player number 1 is always going to be on the left-hand side right here, and the first dollar amount of the first number always goes towards player number 1. So this $1 goes to Diego, this $3 goes to Diego, $0 to Diego, and $2 to Diego once again. The second number that you see after the comma, that always goes towards player number 2, and player number 2 is always going to be denoted on top right here. So this $1 goes to Paola, $0, $3, and $2 to Paola once again. So go ahead and find another person and see whether or not you can come to the correct solution or the Nash equilibrium within the simultaneous move game. So all you have to do is pretend that you're player number 1 right here. You have a choice of saying yes or no. Find another player. They're player number 2. They also have a choice of saying yes or no as well. Remember, this is going to be a non-cooperative game, so you two cannot communicate with one another. Just show them the outcomes of all this game, and then you choose your strategies independently of one another. What do you think is going to be the Nash equilibrium, or the best solution, or the solution to this game that will be correct on an exam? So this is actually a game I play in my face-to-face classes, and what do you think is going to be the most typical outcome? Remember that this game is going to be seen as a non-cooperative game, so these players cannot communicate with one another, so they are making their decisions independently of one another. So player number 1, if he chooses yes, and say player number 2 chooses no, that means player number 1 gets $3, but player number 2 gets $0. So what is going to be the Nash equilibrium, or the solution that would be correct on an exam? Well, when we do this in class, the typical solution that both of these players choose is going to be no and no. So $2 for player number 1 and $2 for player number 2. So for Diego and Paola, they both get $2. However, this is going to become an incorrect solution, and it's going to be incorrect because each of these players could have done better off by choosing a different strategy. So this is going to be the typical solution that I do see in my face-to-face classes, and when we do play this game, I'm very, very sad because that's the most amount of money that I have to give away. But this is going to be an incorrect solution because both of these players are probably thinking about the other player. They think about, hey, what happens if we want to cooperate with one another, but we can't communicate that? So let's go ahead and try to maximize the benefit for both of us combined. However, that does go against the assumption that we built up with game theory. Remember that each of these players, they are very selfish and they only want to maximize his or her own payoff. So here, if you selected this, that would be a very, very incorrect solution. The correct solution, or the Nash equilibrium, would be in this box right here, where both of these players, Diego and Paola, actually choose yes and yes. So this is our true Nash equilibrium. Or the solution that would be correct on an exam. And this is going to be the Nash equilibrium because each of these players cannot do any better by choosing a different strategy. So when I ask players about why they chose no in this sort of strategy, in this sort of choice right here, they typically say that, hey, it's probably going to maximize the outcomes or the payoffs for both of these players combined. However, Diego could have done better by choosing yes instead, because he would have gotten $3 instead of $2, and Paola could have done the same exact thing by saying yes, getting $3 instead of $2. So in this instance, remember that both of these players are trying to maximize their own payoffs, and by doing so, by choosing the best strategies for themselves, they're going to be ending up in this box where each of the players gets $1 each. And this is actually a very specific example of a game called a prisoner's dilemma. Prisoner's dilemma. And the prisoner's dilemma just tells us that each of these players actually get an inferior outcome compared to something that could have been achieved that was cooperative. But remember, as we're building these games up, these games are non-cooperative, so these players cannot talk or communicate with one another. And as we get further along in the discussion about game theory, particularly with these simultaneous move games, we'll come back to this example and see exactly why yes and yes is going to be the Nash equilibrium by using something known as the best response technique. So in the next video, we'll go ahead and break down the strategies of each of these players, use the best response technique in order to show you how we come to the Nash equilibrium and why that is going to be seen as the solution for any game theory game that we take a look at when both of the players move at the same exact time.